Welcome back to another explainer. Today, we're tackling a highly technical and honestly pretty fascinating UI challenge that's absolutely captured the attention of Android developers everywhere. We are talking about the elusive Metaball edge effect in Jetpack Compose. Okay, let's dive into this. Here's a quick roadmap of what we're covering. 1. The Metaball edge concept. 2. The giant blob problem. 3. A custom blur solution. 4. Vertical versus horizontal scrolling. And finally, number 5, why metaballs get messy. Section 1. The Metaball edge concept. Imagine scrolling text smoothly, beautifully melting right into the edges of your screen. It's an incredibly elegant concept, and this brilliantly illustrates exactly where the inspiration comes from. Yuri Skoll, the author of our source material, directly credits designer Sina Samamaki for bringing this super clean idea to Android, even going so far as to call his work works of pure art. But as you might guess, actually recreating this aesthetic programmatically? Well, that's quite the challenge. To actually pull this off in Jetpack Compose, the proof of concept boils down to 3 foundational steps. First up, you add vertical gradient bands near the edges. Step 2, you blur the scrolling object. And step 3, you apply a strict alpha threshold filter. Basically, you're taking sharp shapes, blurring them out, and then using that alpha cutoff to snap them back into sharp focus. Why does this matter? Because that specific combination is literally what creates that sticky liquid illusion. Now, depending on exactly how you tune those steps, you end up with 2 distinct visual behaviors. The melt effect is when the text essentially shrinks and just disappears as it gets near the edges. The gooey effect, on the other hand, is when the text visibly stretches out and physically merges with the edge before it vanishes. Keep those 2 terms in mind because they're absolutely crucial as we look at the hurdles coming up. Section 2, the giant blob problem. So, as elegant as this concept sounds, the default system-level approach fails. And, it fails spectacularly. The pivotal question you're probably asking as a developer right now is, can we just use a regular built-in system blur, like a render effect? It would save us hours of work, right? Unfortunately, the answer to that is a hard no. If you try to apply a standard render effect blur to a scrolling column of text, the entire composable gets blurred all at once. The interaction isn't restricted to just the edges anymore, and your whole screen essentially turns into one unreadable, dark blob. And honestly, it gets worse. The stronger and more visually appealing you try to make that Metaball effect, the more disastrous the result. Why? Because the text actually starts interacting with itself first. Letters start merging with their own shapes and blending into neighboring letters long before they ever even reach the screen edges. It's a complete mess. Section 3. A custom blur solution. Let's move to and see how this builds. To fix this giant blob problem, we're going to need a highly technical, highly localized workaround. And the solution here is a custom AGSL local blur. AGSL lets us write custom runtime shaders to ensure that the blur is applied strictly to the top and bottom edges. The sheer genius of this is that the blur strength progressively increases only as the content enters those specific edge zones. That saves the entire middle of the screen from turning into blurry mud. But, as we all know, custom shaders come with computational costs. Through extensive testing, our source actually found a magic number for performance, and that number is 16. An optimal kernel quality maxes out at a 16 dp radius, which translates to about 17 taps. If you try to push past that into, say, 60 or 100 taps, it becomes way too expensive computationally, and it will severely bottleneck your app. Section 4. Vertical versus horizontal scrolling. Okay, now that we actually have a custom blur, how does orientation impact the overall aesthetic? Well, to get even a somewhat decent result vertically, you are looking at some massive, incredibly fragile tuning. You have to perfectly balance the blur radius, the ASGL application area, the alpha threshold, the max alpha in the gradient bands, and, shockingly enough, the text size. Because text size is defined in scalable SPI units, even a tiny change in the user's system font size can instantly ruin the entire animation. Talk about frustrating. Now, what's really interesting about this contrast is how scrolling directions change everything. Vertically, letters are stacked tightly on top of each other, right? So neighboring letters merge top to bottom into these messy, muddy blobs. But horizontally, it's a completely different story. There's almost no side-to-side letter merging happening in the same way, which leads to a much more stable and way cleaner visual result. That being said, horizontal scrolling isn't exactly a silver bullet. If you're scrolling a row of icons, Delicate elements like thin search, check, or plus icons are highly sensitive. To stop them from completely vanishing or just tearing apart on screen, you have to individually lower their alpha thresholds and carefully reduce the blur radius. It is incredibly tedious work.
Section 5. Why Metaballs Get Messy.
This really brings us to a fundamental design truth. Why is this so insanely hard to get right? Well, just compare metaballs to liquid glass. Glass morphism is visually contained entirely within a single component. It's restricted, it's clean. But the metaball effect, that inherently happens in the negative space between elements. Because it operates outside the safe boundaries of the UI elements, it's just incredibly prone to generating visual dirt and chaos.
So the crucial point is perfectly summarized by a quote from our source. You can't prevent a letter from merging with itself. When you're working with complex shapes like text, the actual physics of the metaball aesthetic create an insurmountable limitation. The exact same mechanism that makes text merge so beautifully with the screen edge is the exact same thing that forces it to eat itself first.
Which leaves us with a final, lingering question to ponder. Is the inevitable visual dirt of metaballs truly worth all this massive technical overhead? We've looked at custom shaders, intricate threshold tuning, and relentless artifacting. It's absolutely a stunning concept, but bridging the gap between a pure design idea and a stable engineering reality is often so much messier than it looks. Thank you so much for joining me for this explainer, and I'll catch you in the next one.